Well, hello there. Well, what's up today? Well, my plan is to talk about something that really matters, and that is the nature and origin of the inertial and gravitational mass. Presumably, all people have some sort of concept and familiarity with mass and gravitation and things like that, and it's introduced, I presume, also pretty early in education. However, if you reach the university level and high level courses, it's like the question how to explain these concepts from fundamental principles. That's then considered as perhaps one of the most profound questions about nature that you can ask. And we're going to explore this topic now. Let's see if we can move on. Now, historically, uh, there was a great emphasis on the distinction between inertial mass on the one hand and gravitational mass. Now, what's inertial mass? Well, it's the mass that resists acceleration. So, for example, if we have a golden wagon here that presumably has a lot of inertial mass, well, then we use, in this case, four horses to drag it along. So in this case, our intuition about the mass is that it will be hard to make it move. We can look at that mathematically. We have Newton's second law. We say that the force is equal to the inertial mass times acceleration, or that the acceleration is the applied force divided by the inertial mass. And then obviously, if the inertial mass is great, then we get a lower acceleration. So if we move on, well, what is then gravitational mass? Well, if you drop an object like an apple or something, then the intuition about the situation is the very opposite, namely that if you have a heavy object that you drop, then unlike in the previous case, your intuition tells you that this will actually acquire a great speed. Um, So yes, the gravitational mass causes the gravitational force according to Newton's law of gravity, which looks like this, where we have the mass of the one big object, we can say, and the mass of a small object divided by their distance squared. But then, as I said previously, our intuition tells us that a massive object will acquire greater speed when we drop it. And for a long time, that was also what many people believed, I presume. And then there's this anecdote with Galileo dropping some object from the Tower of Pisa or something like that, illustrating to an audience that no, I mean, objects, unless they acquire a lot of air resistance, they will actually fall at the same speed. And this we can explain by combining Newton's law of second law with Newton's law of gravitational force. We assume that this force now is some constant c times the product of the masses divided by the distance squared. And additionally assume that the inertial mass for some reason is proportional to the gravitational mass. Well, in this equation, we can then cancel these two m up to some constant, and we arrive at an expression for the acceleration, which only depends on the second object, which, I mean, typically is the Earth or a celestial body. And this is, I mean, a mathematical explanation why objects in principle fall at the same speed, and that is that the inertial mass is proportional to the gravitational mass. Well, today physicists typically speak of the inertial mass and gravitational mass as equivalent quotation marks. It's sometimes phrased as Einstein's equivalence principle. And we will see if, as we move along, if this is really justified. We can just name in passing some of the modern day explanations for the mass. As I mentioned previously, it has been considered as a very profound question, and it's, I mean, in quite recent years that there was this big fuss from the Large Hadron Collider that they had finally found the Higgs boson and inertial mass, as I understand it from modern physics, is that it's explained by elementary particles interacting with the Higgs field. And what about the gravitational mass? Well, I presume the only modern theory, mainstream theory, that attempts to predict gravitational mass is string theory. But I don't know too much about these topics. Other than, I mean, what I've heard. For example, this theory about the inertial mass as being, the interaction with some exotic field, which, I mean, nobody has ever come into contact with in everyday life, combined with the rumor that it isn't that profound. I mean, for example, the question you can ask is, why is the proton 1,800 times more massive than the electron? As a question you can ask. And what answer does this theory give to that question? And I don't think it's more profound than it says that, well, the proton interacts with the Higgs field at a factor 1,800 higher than the electron. So there's nothing more to it. So what I'm going to explore here is something that I bumped into and where it seems to me that both the inertial mass and, as we will see later, the gravitational mass can be arrived at from classical electrodynamics. So we'll see what that means now as we begin with the inertial mass. So here we have a paper by Mario Rabinovitz. You can see the abstract here. What he's going to do is that from classical electrodynamics, he's going to derive an expression for a retardation force. But he also makes a clear distinction that this retardation force is not the same as some kind of dissipation force that is associated with the loss of energy through radiation by an accelerating charged particle. I mean, that's the Larmor formula, that a charged particle that accelerates, it will radiate and hence lose energy. And that could, I guess, be represented as some kind of force. But here it's emphasized that what we're considering here is not any kind of dissipation force. And it is also argued in the paper that this retardation force is very much higher in magnitude than any dissipation force. So I'm going to go through a little bit the derivation. It isn't that long, actually. I mean, it's ingenious to find it, but the calculations in this case is not that complicated. Well, we start with Biot-Savart's law. So if we have a charged particle with a velocity, then that will induce a magnetic field. That's essentially what it's saying here. But if the velocity is time dependent, and that is precisely what acceleration means. Acceleration means that the velocity would change in time. That means that the time derivative of the velocity is not zero. But then we have that, this is the Maxwell-Faraday equation. Then we have that if the velocity varies, then according to the previous Biot-Savart equation, then the time derivative of the magnetic field, it will also be non-zero. So then we induce an electric field. And that electric field will sort of interact with as an opposing force to this electron or charged particle. And then there are some more calculations, and B here is the radius of the particle. Z is the position, and then Z with two dots, that's simply the second derivative with respect to time, and which is acceleration. So if we now imagine that we have this charged particle, we apply an external force, then Newton's second law would say that this external force is equal to the mass times the acceleration. But the point here is that now the author here has derived a retardation force that we need to add, which looks like this. And one first observation, which is kind of interesting, is that we cannot assume that the radius of the electron or proton is zero, because then this expression blows up to infinity. So if we are to accept the validity of this, we actually already at this point need to assume that there exists some kind of radius of the electron. Now, so what is this? Well, the author argues that, well, it's probably something of the quantum wavelength because it's useful in quantum mechanics or something like that. And in that case, we see that this additional mass, which he actually notes here by name, is the rest mass, the conventional mass divided by 137. So it's a small increment if you assume that this is indeed the effective radius of the electron or proton in this case. But then, if we come this far, then I cannot sort of hinder myself from asking the following question. You have some expression times acceleration. So it's standing just next to the conventional mass in this formula. And it's so suggestive now to just assume, well, maybe this is the conventional mass. That would amount to just, canceling, taking away the conventional mass in this formula. Or essentially taking this expression to be equal in magnitude to the conventional mass. So we equate this with this. And the question is then, well, which radius would we get if we take this equal to that? Well, then we get the classical electron radius. So this is practically the same expression as the previous one, where M and R, which has the letter B in the previous formula, have just been sort of switched in position here. We can put that again. So here we see. But of course, this classical electron radius has not been considered in this context before. So I think this is fascinating that we can perhaps derive the inertial mass from classical electrodynamics. So what about the gravitational mass? Well, it turns out that there have been attempts to derive this from electromagnetism as well. So here you see a paper from 1991. Now, I should not pretend that I've grasped all the calculations here because they are quite more cumbersome and extensive than in the previous case. But maybe I can try to extract some major ideas here. They hypothesize that gravitational attraction is essentially an attractive force of the fourth order between two dipoles. Each dipole is supposed to consist of a positive charge in the center and a negative charge oscillating harmonically around the positive charge, as usual. So we're considering a hydrogen atom, maybe a neutron. This paper doesn't exclude the possibility of a neutron. Maybe it's the case that a neutron is an electron oscillating around a proton, even though I would maybe rather assume that it's not oscillating at all in that case, but that's another totally other story. And they come to a good magnitude of this mass, assuming that you have frequencies in the order of, something times 10 to the 9. And this microwave frequency is exactly the kind of frequency that we have on the atomic scale. So essentially what this tells us is that gravitational mass is a phenomena between atoms and not elementary charged particles. So if we just wrap this up, if we assume that these derivations then, none of them were mine, I just reinterpreted a little bit the first one. Well, what can we conclude? Well, then, in that case, inertial mass is a property of charged elementary particles, unlike gravitational mass that is a property of atoms, and possibly also neutrons. But also, I think, interestingly, we see that these inverse square law singularities that are often discussed as a problem in modern physics, well, they do not seem to appear in reality in that case. Because if you think about the gravitational force between two atoms, well, the distance between two atoms cannot really become zero, because then it's no longer two atoms interacting as dipoles. Then you have a completely different situation, and the previous derivation should have sort of diverted in some way long before you even reach anything like two atoms being at a zero distance from each other. Likewise, even if you have two elementary charged elementary particles, well, you have the Coulomb force law that blows up for zero distance. But again, if we require that the particle has some kind of radius, which already this implies in some sense, Well, then again, what does it mean that two particles are at the same position? It can't really be. Although, of course, this needs more elaboration explanation than this at this point, I would argue. But anyway, so that's that. So I will leave you with these, which I find very interesting ideas, and hope to see you some other time in the future soon. So bye bye.